Welcome to Module 2 of the Data Center MEP Testing and Commissioning Playbook. This module focuses on critical aspects such as cooling systems, controls, fire protection, security, and integrated scenarios essential for a reliable data center operation. We'll cover mechanical and controls commissioning, starting from water systems and thermal response, extending through fire protection measures, monitoring platforms, and security logistics, all the way to integrated system testing scenarios. Throughout this module, we'll guide you step by step through various commissioning levels. These include the initial design review, factory acceptance testing or witness inspections, installation quality assurance and quality control, static and pre-energization checks, system startup, site acceptance testing and performance verification, integrated system testing, and finally, handover training. Key training topics you'll dive into include the functionality and commissioning of front water units and CRAH, CRAC, and DX units, direct-to-chip cooling strategies with cooling distribution units, various cooling tower designs, understanding and setting SPLC state points, fire ventilation fan operations, and managing security and logistics interfaces effectively. This module is structured not just as a learning resource, but as an interactive video chapter. You'll be encouraged to teach the material, review the expected evidence, and then pause to engage with test pack examples or real-world field scenarios to reinforce the concepts. By the end of this module, you'll have a thorough understanding of these complex systems and be well prepared to move through the commissioning process confidently. Here's an overview of Module 2 in our Data Center MEP Testing and Commissioning Playbook. This module is structured as a continuation of our training, designed so that each section acts like a chapter marker to guide us through the content clearly and systematically. We start with mechanical pre-commissioning for water systems. This foundational step ensures all water-related components are mechanically ready before moving forward. Then we move on to airside systems, including freshwater units, CDU and direct-to-chip cooling, as well as liquid cooling commissioning, all critical for effective thermal management. Next, we cover cooling towers, heat rejection, and SPLC state points. These elements are vital for maintaining optimal temperatures and system stability. We then focus on fuel systems, leak detection strategies, and monitoring platforms to ensure safety and operational integrity. Fire protection is a major topic, including VESTA smoke detection, hydrant systems, and fire brigade interfaces. We'll also explore fire ventilation fans and smoke control interfaces, essential for emergency response and safety compliance. Security aspects including loading docks, electric overhead traveling cranes, lifts, and material handling are also addressed to ensure smooth, secure operations. Later sections cover heat load testing, integrated systems testing, resilience demonstration, and an integrated register that tracks mechanical, fire, and security elements. A key navigation principle throughout this module is that every test item must link back to a design basis, a commissioning level gate, defined acceptance criteria, a calibrated measurement, and a signed evidence record. This ensures traceability and accountability in all testing and commissioning activities. This structure helps us cover the comprehensive scope of MEP commissioning with clarity and precision. Now, let's dive into mechanical pre-commissioning for water systems. The main goal here is to ensure that both closed and open water systems are clean, pressure-tight, chemically treated, balanced, and fully prepared for a controlled startup. To achieve this, we need a variety of pre-start records including pressure test certificates, flushing reports, water quality certificates, chemical dosing records, valve position schedules, strainer inspection logs, and inspections for insulation and trace heating. Hydronic verification plays a key role and involves checking elements such as pipe supports, expansion loops, flexible connections, drain and vent points, valve access, bypasses, differential pressure points, and confirming flow directions with arrows. Maintaining cleanliness is critical, so temporary strainers, side stream filtration, removing dead legs, ensuring proper flushing velocities, and following strict witness hold points and sample acceptance criteria are essential steps. Balancing controls require calibrated instruments and verifying pump curves, valve authority, coil flow, branch flow records, and producing the final indexed balancing report to confirm everything is correctly balanced. For trace heating and insulation, we test circuit continuity, perform MEGR or IR testing, check thermostat function, ensure insulation finish is intact, and verify proper labeling with maintainable junction boxes. we have two hold points that emphasize safety and quality assurance. No pumps should be started until we have accepted evidence of pressure tests, flushes, chemical treatments, and strainers. And before Level 4 performance testing, all design flow rates and valve positions must be properly recorded. Finally, the table here outlines the evidence required before moving on to Levels 3 and 4 testing for different systems. For chilled water and condenser water, we need pressure, flush, chemical treatment, and tab flow reports. For makeup, RO, and dosing systems, water quality, dosing rates, interlocks, and alarms must be documented. Leak detection requires a zone map, sensor continuity, and alarm interface verification. For pressurization systems, set points, vessel precharge, and pump duty and standby configurations must be confirmed. This structured approach ensures water systems are reliable and ready for operation. Here we're focusing on the cooling equipment coverage, specifically the airside components, fan wall units, and liquid cooling interfaces. The key to successful commissioning in these areas spans from verifying installation quality to ensuring a stable thermal response, setting up alarms, monitoring trends, managing failover scenarios, and enabling operator actions. The table breaks down the commissioning activities into 3 levels for different assets. At Level 2, or CxL2, we check basic mechanical and electrical components like filters, coils, valves, sensors, belts, and isolations to make sure everything is installed correctly and ready for operation. Moving to CxL3, the startup phase, we validate the operation of fans, valves, compressors, and controllers. We confirm safety functionality like frost or condensate alarms and test local and remote commands to confirm proper integration with the building management system. At the highest levels, CxL4 and CxL5, we focus on functional and performance commissioning. This includes verifying airflow rates, temperature and humidity control, free cooling economizers, alarm escalations, and system redundancy or failover capabilities to assure space stability and reliable cooling performance. An important concept is that cooling evidence must create a continuous chain linking the heat source through airflow or coolant flow to heat rejection, and finally to controls response. For liquid cooling, consider the cooling distribution unit and direct-to-chip interfaces as complex hydraulic, controls, and IT load systems all working together. By systematically progressing through these verification steps, we ensure cooling systems not only start correctly, but operate efficiently and safely under different conditions. This comprehensive approach is vital for reliable data center thermal management. Here we focus on the commissioning process for CDU direct-to-chip liquid cooling, which is a crucial aspect of data center MEP testing. The commissioning evidence must comprehensively verify several key areas: hydraulic integrity, coolant quality, leak response, controls integration, and the capture of heat generated by the IT load. Starting with the basics, the facility's chilled water or heat rejection loop feeds into the CDU, which includes pumps, heat exchangers, and controls. From there, the secondary coolant is supplied through headers to the rack manifold quick connects and finally to the direct-to-chip cold plates, with the return coolant completing the cycle. Now, the commissioning process is structured through multiple gates from CxL0 to CxL5, each requiring specific proof. At CxL0, you confirm the foundational aspects like heat density, redundancy of the CDU, fluid chemistry, leak philosophy, rack interfaces, and maintainability. Moving to CxL1, the focus is on witnessing the factory acceptance test for the CDU, including verifying pump curves, controller software versions, sensors, valves, alarms, and communication protocols. At CxL2, both A and B stages involve on-site verification of physical installation details such as placement, access, pipe supports, hoses, manifolds, labeling, isolation valves, leak detection routing, followed by rigorous hydro and pneumatic leak tests, flushing and cleanliness checks, coolant properties, and sensor calibrations. CxL3 confirms system operation by starting the pumps and proving flow, pressure, and temperature parameters, verifying local human-machine interface functionality, alarm systems, valve actuation, automatic restart, and loss of communication behaviors. Finally, at CxL4 and L5, the actual IT or load bank heat is applied. This stage proves crucial redundancy measures such as pump failure protocols, leak alarms, power transfer capabilities, and controls monitoring via BMS or DCAM with trend analysis and recovery testing. It's important to note that simply starting the pumps does not constitute CDU acceptance. The system must demonstrate stable coolant delivery to the rack interface and correctly respond to faults including leaks, power loss, and communication failures to be fully commissioned. This thorough process ensures reliability and operational integrity for the liquid cooling system in the data center environment. On this slide, we focus on the heat rejection and chilled water plant, which includes chillers, cooling towers or dry coolers, pumps, valves, and heat exchangers. Our goal is to ensure that the plant operates efficiently and reliably through thorough testing and commissioning. First, it's important to confirm the plant's capacity at multiple operating points, not just one. This means recording data like entering and leaving water temperatures, flow rates, pressure, power consumption, and ambient conditions. This helps us understand how the plant performs under varying loads. Next, we verify how the system stages and destages its equipment. This involves checking lead and lag rotation, how duty and standby chillers are selected, the criteria for enabling chillers, minimum run times, and anti-short cycle logic to prevent excessive on-off cycling. We also validate redundancy in the system. This includes simulating failures such as pump, chiller, or cooler cell breakdowns, valve failures, and bypass capabilities. The system should handle these faults smoothly without compromising performance. Testing the waterside control loops is another critical step. We confirm functions like differential pressure reset, supply temperature reset, modulation of free cooling valves, and bypass controls to optimize efficiency. Mechanical restart after electrical disturbances is essential as well. We check the plant's ride-through capabilities, the restart sequence, how quickly chilled water temperatures recover, and whether alarms reset properly after an event. Finally, we verify the maintainability of the plant. This means ensuring isolation valves, strainers, drains, vents, access clearances, lifting routes, and safe chemical handling interfaces are all in place for safe and efficient maintenance. Together, these steps ensure a robust and reliable chilled water plant that supports the critical cooling needs of a data center environment. On this slide, we focus on cooling tower variants and the critical aspects of heat rejection commissioning. Cooling towers play a vital role in data center mechanical, electrical, and plumbing systems, and understanding their different types is key to effective testing and commissioning. We have three main types of cooling towers to consider: open circuit, and closed circuit hybrid adiabatic towers. Each type has unique components and testing requirements. For open circuit cooling towers, we look at elements such as the basin, fill, nozzles, drift eliminators, and water treatment processes, including Legionella control. Commissioning tasks include checks for system alignment, fan guards, access, basin coatings, valves, and vibration isolation. Testing also covers basin leaks, fan rotation, variable frequency drives, chemical dosing, and sensor calibrations, with advanced checks on approach temperature, condenser water flow, fan staging, and power recovery. Closed-circuit cooling towers incorporate a closed coil heat exchanger and spray circuits. Key commissioning points include coil access, piping isolation, freeze sensors, spray pumps, and pressure tests. Testing includes hydro and leak tests for coils, fan rotation verification, and monitoring conductivity and freeze protection loops. Advanced tests focus on heat transfer efficiency, delta temperature across the closed loop, fan and spray staging, and alarm responses for freeze or pump failures. Closed-circuit hybrid adiabatic towers combine dry, wet, and adiabatic modes. Their commissioning involves pad frames, water distribution, fan sections, dampers, drainage, and safe access for maintenance. Tests cover spray and pump operations, water quality, anti-scale treatments, and wetting uniformity. More advanced procedures evaluate transitions between dry and wet modes, adiabatic boost performance, water loss fallback strategies, plume and ambient condition monitoring, and recovery times. Best practices for commissioning across all tower types emphasize monitoring ambient dry and wet bulb temperatures, water temperature entering and leaving the system, flow rates, fan speeds, pump status, conductivity, basin water levels, approach temperature, and alarm statuses. These parameters help ensure the cooling tower operates efficiently and reliably under real-world ambient conditions while mitigating risks of failure. Understanding these key aspects allows us to select the right cooling tower type, implement appropriate water treatment, regulate fan and VFD responses, and evaluate heat rejection performance comprehensively. This detailed commissioning approach is fundamental to optimizing data center cooling infrastructure performance and longevity. Here, we see the SPLC state points for the cooling system, which serve as a map to ensure every critical aspect is measured, monitored, and controlled effectively. Each state point corresponds to a specific part of the cooling infrastructure, starting with S1, representing the IT heat or return air. This is where we measure rack inlet and return temperatures, humidity, pressure, and hotspot sensors to confirm the actual thermal load and control of bypass air. Moving to S2, we focus on the CRH or fan wall unit supply air. Here, supply temperature, airflow, fan speed, and valve position are tracked to demonstrate how the airside unit responds to varying loads and possible failures. S3 represents the chilled water supply, where parameters like leaving water temperature, differential pressure, flow, and pump status verify the plant is delivering effective cooling to the coils or cooling distribution units. At S4, the chilled water return, we monitor return temperature and temperature difference to check how well heat is picked up at the coil or CDU and to detect any issues related to low temperature differentials. S5 covers the chiller plant state, including chiller loading, staging, power usage, and alarms. These data points confirm the plant's capacity, redundancy, and the proper sequence during restarts. Finally, S6 pertains to heat rejection, where ambient conditions, cooling tower approach temperature, fan speed, and condenser water parameters are evaluated to validate the system's ultimate ability to reject heat and its sensitivity to weather conditions. An important acceptance rule here is that you cannot declare the cooling stable simply by looking at a single room temperature reading. Instead, the full state point chain needs to be proven, along with the control actions that maintain stability. This comprehensive approach ensures reliability and operational readiness of the cooling system in the data center. Now, let's dive into the key aspects of cooling controls, cool wall systems, and pressurization in data centers. These control systems are critical for maintaining temperature stability, which is essential for reliable data center operation. First, cooling controls and plant managers use features like automatic staging, set point resets, lead/lag configurations, bumpless failover, and PLC redundancy to ensure smooth, uninterrupted cooling operations. To prove these functions work correctly, we rely on trend screenshots, controller logs, and command versus feedback matrices. Next, the CRH network control is tested for group control accuracy, sensor sharing, unit and network failure response, and local fallback modes. Evidence for these tests includes failure scripts, BMS or CMS event logs, and recorded space temperature trends. Cool wall and aisle containment focus on maintaining proper airflow direction, controlling leakage, measuring differential pressure, and ensuring maintenance access is safe and effective. Verification here includes airflow surveys, smoke or visual observations, and pressure readings. Pressurization involves managing duty and standby pumps, setting and monitoring low and high pressure alarms, controlling makeup water, and accommodating expansion. To confirm system readiness, set point sheets, alarm tests, and pump rotation records are reviewed. Finally, water leak detection covers zone identification, sensor and cable continuity, alarm routing, and cause and effect relationships. Supporting evidence includes zone maps, test certificates, and alarm screen captures. An important takeaway is that control acceptance isn't final until every sequence has thorough documentation of commands, feedback, alarms, trend data, and failure mode evidence. This comprehensive proof ensures the system performs reliably under all conditions. Now let's dive into the generator fuel oil system, labeled as D5 in our playbook. This system involves several critical components: fuel transfer, storage, polishing, day tanks, and leak control, all essential to ensure reliable generator operation. First, we need to confirm that the fuel oil system is clean, fully leak-tight, properly labeled, easily accessible, and protected against any cross-connections or uncontrolled releases. Safety and clarity here are paramount. Testing is comprehensive. We check bulk tank level instruments to make sure they accurately reflect the fuel available. Day tank level controls are verified along with transfer pumps, return lines, overflow alarms, leak detection systems, and emergency stop or shut-off mechanisms. Each of these plays a vital role in smooth and safe fuel management. For transfer pumps specifically, we validate the duty and standby pump logic. This includes manual and automatic modes, ensuring that low-level starts and high-level stops are functioning correctly. We also look at high alarms and failure alarms to confirm they trigger appropriately in critical conditions. We thoroughly validate the generator's fuel demand characteristics. This means testing consumption at full load, confirming usable tank volumes, and ensuring refueling interfaces are operational. The polishing and filtration systems are examined as well, along with maintaining sample quality records to monitor fuel integrity. Containment measures get their due attention, too. We verify bund capacity, ensure drain isolation works correctly, confirm leak sensor routing, and check both local alarms and monitoring system alarms for prompt issue detection. Finally, we capture as left valve positions, set points, alarm tags, and finalize the maintenance isolation strategy for ongoing operational safety and ease of maintenance. In summary, this methodical testing and commissioning process ensures the generator fuel oil system operates efficiently, safely, and reliably throughout its service life. Here, we're looking at a mechanical cooling schematic designed for training purposes, focusing on how heat is efficiently removed through the system. The key takeaway is that commissioning doesn't just evaluate the cooling capacity at the plant level. Instead, it follows the entire process from the initial heat source, like the IT equipment or load bank, all the way to the final heat rejection point. Starting at the IT or load bank heat, we monitor the load profile and space trends to understand the heat generated. This heat then moves through the airside units, where airflow, coil temperature differential, and fan or variable frequency drive performance are critical factors. Next, the chilled water loop controls flow, differential pressure, and water quality, essential elements ensuring effective cooling. At the cooling plant, we focus on capacity, staging, and redundancy to maintain reliable operation under varying loads. Finally, heat rejection depends on ambient conditions, approach temperatures, and the performance of fans and pumps. The commissioning process uses a detailed handoff and loop test script that captures both the thermal outcomes and the control actions behind them. This includes set points, staging sequences, alarms, recovery times, and operator indicators, providing comprehensive evidence of system performance throughout. This approach ensures that every node in the cooling path is operating as intended, leading to a reliable and efficient data center cooling system. Here we focus on the critical platforms and networks involved in data center management, including BMS, EPMS, CPOS, DCM, and other monitoring systems. Each platform has a specific commissioning scope and requires distinct acceptance evidence to ensure proper functionality. For example, the building management system involves controlling HVAC components like valves, fans, and sensors. We verify its effectiveness through point-to-point checks, sequence of operations proofs, trend exports, and alarm routing tests. The facility monitoring system tracks the status of critical mechanical, electrical, and plumbing equipment. We confirm its reliability via end-to-end alarms, dashboard screenshots, and event timestamps. Power monitoring includes metering, breakers, generators, UPS systems, and energy performance indicators. Acceptance involves meter mapping, power quality events, load profiles, and power usage effectiveness snapshots. Battery monitoring focuses on cell voltages, temperatures, and alarm thresholds. We validate this by baseline reports, alarm verification, and confirming communication integrity. Operations platforms like DCM handle asset data, capacity, alarms, maintenance records, and user training. Acceptance evidence includes comprehensive asset databases, adherence to naming rules, and successful user acceptance testing. Communication networks require validation of redundant paths, network mapping, failover capabilities, and time synchronization through loop failover tests and reviewing backup configurations. A key point to remember is that a monitoring point isn't truly complete just by showing up on a screen. It must be verified end-to-end, from the physical event through the controller and network components, all the way to alarms, trends, timestamps, and operator responses. This holistic verification is crucial for resilient and effective data center operations. This slide breaks down the controls and monitoring data architecture fundamental to the commissioning process. Starting with field devices, we have sensors, actuators, and meters, which are the physical components that detect or influence conditions in the data center environment. These devices feed information to controllers, typically programmable logic controllers or direct digital controllers, as well as local panels. Next, the network layer consists of switches, rings, and firewalls that ensure secure and efficient data communication between devices and systems. Above that, the platform layer includes building management systems, central management systems, energy management systems, as well as data center infrastructure management and computerized maintenance management systems. These platforms collect, analyze, and display data to operators. Operator interaction involves responding to alarms and following standard operating procedures to maintain optimal performance and respond to issues. A critical aspect emphasized here is the required proof chain for every vital point in this architecture. This proof chain includes the physical trigger, the controller's state, the network path, the screen or alarm display, trend analysis or data export, and ultimately, the operator's action. This comprehensive traceability ensures accountability and confirms that every step in the monitoring and control process is verifiable. This slide focuses on life safety systems, specifically suppression and fire protection, highlighting the essential steps and considerations during commissioning. First, it's critical to adhere to all local authority regulations, fire codes, insurer mandates, and project-specific requirements. Importantly, witness testing must be conducted in a way that never compromises life safety or damages equipment. We need to verify several key components. Zone identity ensures that the correct areas are protected. Hydraulic and pneumatic integrity checks confirm that the systems are functioning properly. Valve supervision, flow and tamper alarms, pressure switches, releasing panels, and any abort or hold devices installed must all be tested thoroughly. An essential part of commissioning is proving the cause and effect interfaces. This means confirming the automatic responses between fire alarms, building management systems, security or access control systems, smoke control measures, shutdown mechanisms, hold open dampers, and notification devices all work seamlessly in coordination. It's also vital to confirm that all rooms, risers, and plant areas have up-to-date and accurate documentation, including drawings, labels, isolation maps, and clear procedures for impairment and reinstatement. Collecting the right paperwork is key to finalizing commissioning, such as certificates, authority inspection records, as-built zone drawings, valve status sheets, and alarm screenshots. Looking at the table, you can see typical evidence for different fire suppression systems. For sprinklers and pre-action systems, we verify valve supervision, flow alarms, air pressure, and the release sequence. Water mist systems require checks on pumps or skids, bottle and tank status, release and abort functions, and zone discharge logic. Clean agent systems focus on bottle pressure, release paths, room integrity, and abort or hold controls. Fire pumps and tanks require flow tests, jockey pump operation, responses to power failure, and controller alarms. Finally, impairment control involves permits, fire watches, isolation tags, and proof of reinstatement. All these steps ensure that life safety systems will perform effectively, protecting both building occupants and critical infrastructure. On this slide, we're focusing on life safety systems, which include alarm, smoke control, and emergency lighting. These systems are critical because they ensure safe detection, notification, and evacuation in case of an emergency. Specifically, we're looking at integrated proof of detection, notification, egress, and plant response, which means verifying that all these components work together seamlessly during an incident. Let's break down the key systems involved and their corresponding testing stages. For the fire alarm system, key checks at levels 2 and 3 include testing detectors, manual call points, modules, panels, proper labeling, and batteries. At higher levels, levels 4 and 5, we focus on integrated proof such as cause and effect verification, alarm communication with building management or central monitoring systems, security interface, and reviewing event logs for accuracy. Moving to smoke extract and pressurization, initial tests confirm fan operation, dampers, controls, fire-rated cable integrity, and local isolation. At advanced levels, we verify mode changes, fan duty and standby roles, interlocks, and the response of smoke zones to ensure proper containment and evacuation paths. Damper controls are checked for correct actuator types, fail-safe positions, feedback from end switches, and access panels during early testing. The integrated proof involves confirming command and feedback signals, response to power loss, and fire mode sequencing to keep fire zones isolated effectively. Emergency lighting testing covers circuit identity, battery and inverter status, checking light levels and duration of operation. Later stages simulate failures to ensure alarms trigger correctly, reports are generated, and exit routes are adequately illuminated. Lastly, the security interface involves testing door release and lock strategies, egress routes, monitoring alarms, and verifying fire mode operation, restoration, and operator acknowledgements. It's important to understand that integrated testing is not just about the fire system triggering an alarm. The correct, successful outcome means every related mechanical, electrical, and plumbing system, along with access controls, smoke control, and monitoring responses, act exactly as defined in the approved cause and effect matrix. This integration ensures a coordinated and efficient response in emergencies, ultimately safeguarding people and assets. This slide focuses on the commissioning process for fire ventilation fans and their smoke control interfaces, which is critical for ensuring safety in data centers. The key here is to commission the entire chain of components, starting from the fire alarm trigger through the fan, duct, damper, and control responses, followed by verifying pressure or smoke clearance evidence, and finally ensuring the system can properly reset after an event. We see a clear flow from the fire alarm control and extraction trigger to manual overrides within control panels or PLCs, alongside the fan starter or variable frequency drive status and fault monitoring. It continues through the air handling components like fans, ducts, and dampers, all forming the smoke control path. Integral to this system is the feedback loop from the building management system and fire alarm system, which track trend data and event logs to confirm operational integrity. The table breaks down the functional and interface proofs required for different systems. For smoke extract fans, for example, we verify fan rotation, airflow paths, damper positions, and modes, alongside fire alarm commands, BMS status, and reset logic. Stair pressurization fans require validation of pressure differentials, VFD responses, and door behaviors, as well as fire alarm commands and sensor trends. Fire lift lobby and shaft pressurization systems also include checks on pressure levels, fan and damper positions, manual override records, emergency power, and fault alarms. The acceptance rule highlighted here mandates that every fire ventilation test must comprehensively cover each component: fan, duct, damper, controller, fire alarm interface, emergency power supply, BMS/FAS feedback, and the manual reset function. This ensures the system will operate effectively and safely during an actual fire event, protecting occupants and critical infrastructure. Here we have an example of a cause and effect matrix used for life safety verification in data center MEP testing and commissioning. This matrix outlines the key triggers or events, like a smoke detector activating in the data hall or a clean agent release, and maps out their coordinated effects across different systems. For instance, when the smoke detector senses an issue, it triggers a fire alarm, sends a critical alert to the building and central monitoring systems, releases egress controls as designed, adjusts HVAC and smoke control equipment accordingly, and ensures no unintended power trips occur. Each row specifies what should happen across fire alarms, building management systems, access control, HVAC, smoke control, and power supplies to maintain safety and operational integrity. It's crucial that this project-approved matrix is used as a template and that every critical scenario is thoroughly tested during later stages, specifically levels 4 and 5, to confirm all systems respond properly and work together seamlessly in an emergency. This approach helps ensure the life safety systems function as intended, protecting both people and infrastructure. Here we have the Integrated Commissioning Item Register for mechanical and data hall support. This register is derived from the original commissioning item list and forms part 1 of the mechanical scope integration. You can see various assets listed here, including chillers, pumps, thermal storage tanks, and hydronic piping systems, each with specified quantities and associated commissioning levels ranging from CxL1 to CxL5. For each asset, there are representative task pack evidences, such as factory tests, visual inspections, technical parameter checks, and specialized tests like MPI for piping. This level of detail ensures thorough validation and quality control during the commissioning process. It's important to use this register as a key planning and control tool by assigning a unique tag to every asset. Each item should also have an associated test pack, clear ownership of evidence, defined witness levels, and a process for issue closure. This approach guarantees traceability and accountability, helping to maintain high standards and smooth execution throughout the mechanical commissioning phase. On this slide, we're focusing on the Integrated Commissioning Item Register for mechanical systems and data hall support, specifically relating to data center MEP testing and commissioning. Key components like fans, ductwork, staircase pressurization systems, LCP fans with variable speed drives and motor starters, plus fuel storage and transfer systems are carefully planned and controlled through this register. You'll notice that for each asset, we list quantities and the commissioning levels applicable, ranging from CX Level 1 through Level 5, as well as TMS-defined standards. The representative task pack evidence includes visual inspections and technical parameter checks to ensure everything meets the required specifications. Importantly, this register serves as a critical planning tool. Every asset must have a unique tag, a defined test pack, an assigned evidence owner, a witness level, and a clear path for closing any issues that arise. This structured approach helps us maintain thorough documentation and accountability throughout the commissioning process, ensuring that all mechanical and data hall support systems function reliably and efficiently. Here we have the Integrated Commissioning Item Register, specifically for public health and water support systems. The key point here is that these systems are included in our commissioning process only when they support critical operations or ensure compliance with relevant codes. Looking at the table, it outlines the main assets involved, such as water treatment systems, plumbing related to the data center, and sewage treatment plant systems. For each asset, the table lists the quantity, the commissioning levels they go through, from Level 2 up to Level 5, and the type of evidence we gather during testing. This evidence includes visual inspections and checks on technical parameters, among other tests like verifying control system points and testing the functionality of sanitary fixtures. It's essential to use this register as a planning tool. Every asset must have a unique tag, a test pack detailing the required checks, an assigned evidence owner, a designated witness level for oversight, and a clear process for closing out any issues found. This structured approach ensures thorough verification and accountability throughout the commissioning of public health and water support systems. In this section, we're focusing on the Electrical Power Monitoring System Commissioning, or EPMS-CX. The main objective here is to ensure that the electrical power monitoring data we collect is accurate, synchronized in time, and truly useful for diagnosing any incidents that may occur. The commissioning scope includes verifying power meters, power quality monitors, breaker statuses, and data from generators, UPS, and automatic transfer switches. We also check gateways, switches, historians, dashboards, and alarms to make sure all data flows correctly. Key parameters like kVA, kilowatts, power factor, total harmonic distortion, waveform captures, and event records are all part of this scope. Additionally, integration with data center infrastructure management, building management systems, and operational reports is critical for a comprehensive view. We apply a level gate proof process, starting with L0, which covers meter hierarchy, data models, time synchronization, and report formats. Moving to L1, we perform factory acceptance tests and point simulations on panels and gateways. L2 splits into L2A and L2B, focusing on wiring, labeling, network paths, and point-to-point verification, including current transformer ratios, polarity, and scaling. L3 involves validating meters under energized conditions and ensuring timestamps are correct. Finally, L4 and L5 cover source transfer tests, waveform captures, and constructing a precise event chronology. For acceptance evidence, documentation is key. We gather meter validation sheets, central time/Pacific time ratio records, and an EPMS point list supplemented by dashboard screenshots. Event logs exported from utility failure or load transfer tests provide crucial proof. Reports on network time protocol and precision time protocol synchronization, along with historian retention confirmation, form part of the package. Operator acceptance and standardized report templates complete the evidence trail. A common trap to avoid is relying solely on screenshots. Power monitoring must demonstrate the actual sequence of events to be effective in incident diagnosis. So, comprehensive data capture and verification are essential to deliver reliable and actionable information. This slide outlines the comprehensive approach we take in the testing and commissioning of the CPOS chiller plant optimization system. The main objective here is to demonstrate that the optimization enhances system stability without sacrificing redundancy or compromising the building's thermal envelopes. Starting with the scope, the commissioning covers the CPOS server and controller, along with all critical components like chillers, pumps, towers or dry coolers, and valves. We monitor a range of sensors including temperature, pressure, flow, power, and status indicators. Essential features such as optimization modes, operational limits, fallback procedures, and manual overrides are also thoroughly tested. Integration with the building management system and DCM tools, as well as thermal trend analysis, are included to ensure comprehensive oversight. The process is structured into multiple level gates. At level 0, we verify the statement of operations, set points, safe limits, and failure fallback strategies. Level 1 focuses on logic emulation, factory acceptance testing, and locking the controller version to maintain consistency. Level 2 is divided into 2 parts. 2A validates sensors, panels, networks, and power supply, while 2B checks loop functionality, calibration, and the commands for valves, fans, and pumps. Level 3 confirms the local plant operation with a stable PID controller response. Finally, levels 4 and 5 test system behavior under partial and full loads, including handling equipment failure and recovery scenarios. Acceptance evidence includes functional scripts with clear pass or fail criteria, trend data for supply and return temperatures, flow rates, and energy usage. We also rigorously test alarms, fallback mechanisms, and manual overrides, supported by records of failure scenarios such as loss of chillers, pumps, or towers. Training ensures operators understand limits and the rules governing overrides. A key caution highlighted is that optimization must never override system resilience. Fail-safe fallback features must be fully tested and validated before integrated systems, testing to avoid any risk to system safety or reliability. This thorough, staged approach ensures the chiller plant operates efficiently, reliably, and safely under all conditions. This slide focuses on the DCM commissioning process as part of our MEP testing and commissioning playbook. The objective here is to ensure that the DCM data is fully trusted for managing capacity, assets, alarms, and handovers. The commissioning scope includes several critical elements. We need to verify the asset hierarchy, naming conventions, and the organization of rooms, racks, power chains, and cooling zones. Capacity data such as power, cooling, space, and network attributes must be accurately represented. Additionally, alarms and trends from various systems like BMS, EPMS, CPOS, and environmental monitoring are part of the scope. User roles, workflows, reports, and metadata related to handovers are also key components. Next, we have the level gate proof process, which breaks down into multiple stages. At level 0, we confirm the data model, integration architecture, and naming standards. Level 1 involves demonstrating platform configuration or factory settings where applicable. Level 2 is split into 2 parts: asset upload, network readiness, and access controls at 2A, and data mapping, import validation, and alarm routing at 2B. Level 3 focuses on live data verification and reviewing operator dashboards. Finally, levels 4 and 5 cover event correlation during failure tests and generating capacity reports. For acceptance evidence, we require several documentation and verification artifacts. This includes asset upload quality reports with traceability checks, records of point mappings and alarm acknowledgements, proof of role-based access controls and audit trails, screenshots and reports showing event correlation, and confirmation of operations user acceptance and training completion. Lastly, a common trap to watch out for is prematurely considering DCM commissioned before there is clear traceability from the asset in the system, through the physical device, all the way to live alarms and trends. Without this, the data cannot be fully trusted for operational use. On this slide, we're looking at the controls and data platform integration schematic, which is a crucial part of the MEP testing and commissioning process. The key concept here is that the commissioning proof must trace the signal all the way from the field device, through the network and platform layers, and finally to the operator's response. Starting at the bottom, we have the field devices like meters and sensors that generate the initial data. This data is then processed by controllers such as PLCs, DDCs, or ACMPs. From there, it travels over the OT network, which has redundant A and B paths to ensure reliability. The data reaches various platforms, including BMS, EPMS, CPOS, and DCM, each serving a specific function from building management to asset control. Ultimately, this information is utilized by operations centers like SOC, NOC, or FM. The slide breaks down the commissioning proof into 3 types. First, point-to-point proof involves creating a physical event at the source, confirming that controller inputs and outputs respond as expected, verifying network path and timestamps, and ensuring that alarms, trends, and dashboard updates are accurate. Second, integration proof focuses on validating that each platform performs its role correctly. BMS confirms HVAC logic, EPMS verifies electrical event sequences, CPOS ensures optimized plant control, and DCM demonstrates asset and capacity linkage. Finally, failure proof is about testing the system's resilience by simulating scenarios such as controller loss, network failover between A and B paths, gateway restarts, and handling bad or out-of-range values with appropriate alarms. This thorough approach ensures the entire control and data system operates reliably and as designed. Here we have an integrated commissioning item register specifically focused on fire, alarm, and monitoring platforms within the data center MEP testing and commissioning playbook. This register consolidates key systems such as fire pumps, fire hydrants, various sprinkler systems, fire alarm systems, smoke detection, building management systems, electrical power monitoring, and critical power management. Each asset is assigned specific commissioning levels, ranging from CxL1 through CxL5, indicating the depth and rigor of testing required. For example, fire pumps undergo multiple commissioning levels, including mechanical testing to verify proper alignment and coupling between the motor and pump. Most other systems, like sprinkler systems and fire alarms, emphasize visual inspections and technical parameter checks to ensure functionality and compliance. The data here transforms these system rows into detailed point-to-point, commissioning, and evidential tasks that guide both testing and operational response. Importantly, you should use this register as a planning control tool. Every asset listed must have an associated tag, a corresponding test pack, a designated evidence owner, a witness level to confirm proper oversight, and a clear path for issue closure. This structured approach ensures thorough tracking and accountability throughout the commissioning process, enhancing safety and reliability in the data center's critical fire and monitoring infrastructure. On this slide, we focus on the generator fuel system and its fuel polishing commissioning. The main goal here is to ensure that clean fuel is always available to generators during standby, transfer, polishing, and emergency operations. This is critical to reliable generator function when power is needed most. The commissioning scope covers several components: bulk storage and day tanks, transfer pumps and valves, the fuel polishing skid along with its filters, sensors, and control system including PLC and HMI. We also verify fuel level monitoring, leak detection systems, interlocks, alarms, and the generator's demand response, refill sequence, and manual bypass capabilities. The process follows a level gate proof strategy. Starting with L0, which involves confirming NFPA, SNI, and local code compliance regarding fuel strategy, runtime, containment, and quality. L1 includes factory acceptance testing of tanks, pumps, skids, and control logic. L2A and L2B focus on installation details like pipe support, labeling, containment, ventilation, pressure and leak tests, valve verification, and cable checks. L3 validates pump rotation, polishing cycles, and establishes a fuel quality baseline. Finally, L4 and L5 confirm generator demand triggers. Low fuel alarms, pump failure detection, and leak alarms are all functioning properly. The acceptance evidence is comprehensive, ranging from fuel quality reports and baseline filter conditions to pressure and leak test documentation. It also includes control system inputs and outputs, alarm integration with building management and emergency power monitoring systems, generator refill sequence trends during load testing, and finalized operational procedures for polishing and fuel sampling. A common pitfall to watch out for is assuming fuel polishing readiness is proven without testing fuel quality, control systems, and generator demand collectively. Only by confirming all these elements work together can we be confident the fuel system will perform reliably when it counts. On this slide, we're comparing water leak detection with fuel leak detection, highlighting why these systems must be treated as separate risk controls. Each uses different sensors, response actions, and acceptance criteria because they address distinct hazards. For water leak detection, the primary risk is water damaging critical electrical rooms and cooling systems. The sensors typically include water-sensing cables or probes, zone modules, and room sensors placed in areas like data halls, cooling units, chilled water pipework, condensate lines, and wet risers. The Level 2B test involves checking continuity, simulating water contact, and ensuring a proper dry reset. The response is integrated with building management or data center infrastructure management systems, triggering alarms and local alerts, and potentially activating valves or pumps if built into the design. To accept the system, you need evidence such as zone maps, alarm screenshots, reset records, and confirmation that the area is dry. In contrast, fuel leak detection focuses on hydrocarbon release risks that could affect fire safety, the environment, and generator reliability. Sensors here include hydrocarbon probes and cables, tank interstitial sensors, and sump or interceptor sensors installed around underground storage tanks, fuel transfer pipes, pump skids, polishing skids, and generator rooms. The testing involves continuity checks, hydrocarbon simulation, interstitial alarm verification, and a safe reset process. Responses are tied to fuel management PLCs or building systems, enabling pump shutdowns and environmental safety protocols. Acceptance evidence must include leak zone maps, records of safe simulation tests, pump interlock confirmations, and documented incident response procedures. Understanding these differences ensures each system is commissioned effectively to manage its unique risks. This slide focuses on the air-cooled load bank test commissioning, which aims to verify that generators, UPS, and STS systems can handle step load testing while safely rejecting heat into the air. The scope includes using portable or containerized resistive or reactive load banks, equipped with cam locks, cables, remote controls, step contactors, and emergency stops for safety. It's crucial to ensure proper air discharge paths, adequate hot air clearance, and effective fire safety and noise control measures. We also monitor electrical parameters and capture waveforms and events through EPMS or PQM systems. Verification is broken down into level gate proofs, starting with the test plan and safety controls, followed by factory calibration certificates for the load bank. Then we check connection labels, cable routing, exclusion zones, insulation resistance, emergency stops, fan rotations, and communications. This progresses to low-load energization and control checks, finally moving through step loading at various intensities and load rejection or transfer scenarios. Acceptance evidence includes detailed load step logs with calibrated meter readings, thermal scans at cables, bus ducts, and switchgear, alongside observations on air temperature, noise, and safety. Event exports and waveform captures are collected, and a certificate is issued confirming damage-free disconnection and reinstatement. A common pitfall is air discharge recirculation, which can skew thermal readings, so it's essential to confirm the air path is clear before full load testing begins. This slide focuses on the water-cooled load bank test commissioning process. The main objective here is to confirm that load testing can be performed safely without air heat recirculation, while ensuring the heat rejection water circuit is protected. The commissioning scope includes several key components: the water-cooled load bank, heat exchanger, and valves, along with temporary and permanent water connections, strainers, and flow meters. It also covers electrical cam locks and cables, controls, safety interlocks, and the heat rejection system, whether through chilled water, condenser water, or a dedicated water loop, depending on the design. To validate the process, we rely on a series of level gate proofs. These start with the hydraulic design, verifying heat rejection capacity and isolation strategies at level 0. Then, at level 1, we perform factory acceptance testing and calibration of the load bank and controls. Level 2 is split into two parts. 2A looks at pipe supports, hoses, drains, pressure ratings, and electrical routing, while 2B involves hydro and leak testing, flow proving, insulation resistance, continuity checks, and emergency stop functionality. Level 3 focuses on low-load energization and alarms for flow and temperature. Finally, levels 4 and 5 deliver staged full load testing, including checks for water flow failure and high-temperature trip validation. For acceptance evidence, we collect data such as hydro and leak test results, flow and temperature trends, electrical load logs, and records from energy performance monitoring systems. Interlocks are tested for conditions like low flow, high temperature, pump failure, and emergency stop. Thermal scans are also performed to check connections and valves, followed by thorough drain, cleanup, and reinstatement documentation. A crucial point to remember is that water-cooled load tests must commission both the electrical load and the hydraulic heat rejection system together, treating them as a single integrated system. Overlooking this can lead to common pitfalls during commissioning. Now we're focusing on Section D, which covers fire protection, detection, and firewater systems. This section highlights key aspects such as hydrant functionality, fire brigade readiness, firewater supply, and air sampling detection commissioning. These elements are critical for ensuring that fire safety systems are fully operational and effective during emergencies. The testing and commissioning procedures followed here come from our MEP testing and commissioning playbook, providing a structured approach to verifying that all fire protection measures are in place and functioning as designed. This ensures safety compliance and readiness for any potential fire incidents. On this slide, we're focusing on the commissioning process for ASD or VESTA air sampling smoke detection systems. The main objective here is to ensure that the air sampling smoke detection is properly zoned, sensitive enough, effectively transporting air samples, and fully integrated into the overall fire strategy. First, let's talk about the commissioning scope. This covers everything from the physical detector units and their associated sampling pipe networks, including end caps and aspirators, to the finer details like detector zones, pipe holes, labeling, filters, and airflow monitoring. It also involves verifying the fire alarm panel, building management system alarms, and making sure the cause and effect matrix is accurate. High sensitivity is especially important in critical areas like data halls and electrical rooms, which require very high detection standards. Next are the level gate proofs, which are step-by-step verification stages. Level 0 involves checking coverage, sampling calculations, alarm levels, and the cause and effect design. Level 1 covers factory testing of panels and detectors, as well as software setup. Level 2 is split into two parts, verifying pipe routing, holes, labels, and access first, then checking pipe integrity, airflow, transport time, and point mapping. Level 3 involves smoke simulation tests, checking fault alarms, and confirming detector thresholds. Finally, Levels 4 and 5 address integration with fire strategy, HVAC or fan responses, and how alarms are routed throughout the system. Acceptance evidence is crucial for sign-off and includes a range of documentation such as sampling calculations and as-built pipe drawings, tests on transport time and airflow, alarm and fault screenshots with fire alarm system event logs, detailed cause and effect test sheets, and records of system resets. It's also essential that operators receive training on isolating the system and maintaining filters properly. Lastly, watch out for common traps. Even though ASD and VESTA terminology is used in training, the commissioning evidence must always align strictly with the approved detector types and the design calculations that were signed off. This ensures that the documentation and testing are accurate and compliant with the approved fire safety plan. Overall, this structured approach ensures that the air sampling smoke detection delivers reliable, sensitive, and timely detection of smoke as part of the building's comprehensive fire protection strategy. This slide outlines the key aspects of commissioning the hydrant system, ensuring both indoor and external hydrants meet essential performance criteria. The main objective here is to verify that hydrants deliver the necessary flow and pressure, are accessible for use, and have proper fire alarm supervision integrated. Starting with the scope, the commissioning covers the entire indoor hydrant and hose reel network, as well as the external hydrant ring. It also includes critical components like valves, landing valves, cabinets, signage, and hose connections. Beyond that, fire pumps, tanks or headers, flow meters, and pressure gauges are tested. Supervised valves, tamper and flow alarms, along with the fire command interface, are also under scrutiny to confirm they are functioning correctly. The process is broken down into a series of level gate proofs, each targeting specific stages. At the initial level, L0, hydraulic calculations, zoning verification, flow and pressure assessments, and compliance with AHJ and safety standards like NFPA are reviewed. Moving to L1, factory acceptance tests for pumps, skids, and valves are conducted when applicable. L2 is split into two parts. L2A focuses on physical installation checks such as pipework, supports, and signage, while L2B deals with functional tests including flushing, hydrostatic pressure testing, valve supervision, and gauge calibration. Level 3 involves operational checks like starting the pump, operating local valves, and capturing pressure readings. Finally, levels 4 and 5 cover flow testing, integration with the fire alarm system, and verifying operation during power failure. Acceptance evidence must be thorough and clear. This includes reports from hydrostatic and flushing tests, documented flow and pressure results from representative hydrants, and screenshots or logs demonstrating valve, tamper, and flow alarm activity. Records from the fire pump controller and its power source are essential, as is witness sign-off from AHJ authorities when necessary. A common pitfall to watch out for is remembering that hydrant commissioning isn't just about hydraulic performance. It equally demands proving operational accessibility, ensuring that all components can be reached and used effectively in an emergency. This comprehensive approach guarantees the hydrant system is fully reliable and compliant. This slide covers the commissioning process for the fire brigade inlet and city water fire truck outlet in our MEP systems. The main objective here is to ensure that emergency service connections can effectively fill the system header and support fire truck filling whenever required. The scope of commissioning includes verifying the fire brigade inlet and city water fire brigade outlet or filling point for the fire truck. We need to check all associated components such as check valves, isolation valves, signage, caps, drains, and backflow control mechanisms. It's also critical to assess pressure gauges, flow paths, accessibility, and vehicle approach to ensure everything functions smoothly during an emergency. We follow a detailed level gate proof approach. Starting at level 0, we confirm the connection type, thread, pressure, and flow criteria meet standards like SNI, NFPA, or the authority having jurisdiction. Level 1 involves reviewing factory certificates for valves and fittings where relevant. Level 2 is split into 2 sections. 2A focuses on location, signage, access, pipe supports, and valve orientation. 2B covers flushing, hydrostatic testing, check valve direction, and drain verification. Level 3 moves into operational checks such as connection operation, cap removal, backflow and drain functionality, and local indicators. Finally, Levels 4 and 5 simulate actual fire service filling, including fire pump and header interface testing along with alarm verification. For acceptance evidence, we gather reports on hydrostatic and flushing tests along with valve inspections. We also document flow and pressure tests from the inlet through to the header and record inspections of outlet accessibility and signage. Check valve, backflow, and drain test results are compiled, and if necessary, we include witness records from the authority or fire brigade. It's important to note a common pitfall. The inlet and outlet have distinct functions. The inlet is designed to fill the facility header, while the outlet is intended to fill a fire truck or an external response resource. Understanding this distinction helps avoid commissioning errors that can impact emergency readiness. On this slide, we're focusing on the commissioning of fire pump and fire water infrastructure, which is critical for ensuring fire safety systems operate reliably during emergencies. The main objective here is to demonstrate that the fire water supply, pumps, and controls can effectively support sprinkler systems, hydrants, and brigade operations, whether under normal power or emergency power conditions. The commissioning scope includes several key components. First, the fire water tank, jockey pump, and both electric and diesel fire pumps along with their controllers must be included. Next, the combined sprinkler and hydrant headers, together with test lines, relief valves, and flow meters, are essential parts of the system to verify. Also, we must consider power supplies, generator interfaces, alarms, and remote monitoring to ensure seamless operation during power outages or failures. Lastly, the physical environment such as pump room ventilation, drainage, signage, and access needs to be checked to comply with safety and operational standards. The level gate proof steps help break down the commissioning process into manageable stages. At level 0, we verify hydraulic demand, pump sizing, power source, and control basis, which sets the foundation. Level 1 involves factory acceptance testing of the pump and controller, along with reviewing pump curves and certificates. Level 2 is split into 2 parts. 2A covers installation, alignment, suction and discharge points, tanks, and valves, while 2B focuses on hydrostatic testing, flushing, rotation tests, controller wiring, and alarm points. Level 3 includes functional checks such as churn tests, start/stop operations, jockey pump function, and controller alarms. Finally, levels 4 and 5 deal with flow testing, simulating power failures, generator operation, and demand scenarios to validate the system's performance under real incident conditions. For acceptance evidence, we need detailed reports and data. This includes pump curve and flow test reports, event logs from controllers showing alarms and statuses, documented proof of power failure and generator transfer events, and trends of tank levels, valve supervision, and header pressures. Additionally, evidence of operations training and impairment procedures ensures personnel are prepared to manage the system effectively. A common trap to watch out for is focusing solely on hydraulic flow during commissioning. It's important to also include power source failure behavior in the testing to fully understand how the fire pump system will respond during actual emergencies. This comprehensive approach ensures fire protection systems are dependable when they matter most. Now we're moving into Section D, which focuses on security, logistics, and material handling. This part covers the commissioning scope for high-security perimeters, ensuring that all access points are controlled and secure. We also delve into logistics access, including loading dock equipment and the systems required for heavy lifting. To guide us through these processes, we'll be using the MEP Testing and Commissioning Playbook, which provides a structured approach to ensure everything functions safely and efficiently in these critical areas. Now, let's focus on commissioning the external security system, which is a critical layer of protection for any facility. The commissioning process involves more than just installing equipment. It's about ensuring that all physical security measures operate seamlessly as layered barriers. These include controlled entry points, monitored events, and emergency response modes. Starting from the perimeter, we have the fence equipped with perimeter intrusion detection systems and CCTV coverage to monitor and secure the outer boundary. Moving inward, vehicle access is controlled through crash-rated gates, arm barriers, and road blockers, which are designed to stop unauthorized or unsafe vehicle entry. For pedestrian access, full-height turnstiles and speed gates ensure controlled passage, usually supplemented by screening measures such as X-ray or search stations. The mantrap or lobby area uses access control systems combined with CCTV and intercoms to validate identity and prevent tailgating or unauthorized entry. Finally, the Security Operations Center or Network Operations Center manages alarm responses and monitors all security-related activities in real time. The commissioning scope covers all these components, verifying that each part, from fences and lighting to advanced access control and guard workflows, is functioning correctly. Testing focuses on a range of critical events, including normal access, denied attempts, forced or held open doors, emergency egress scenarios, vehicle interlocks, and camera operations like recording, retention, and alarm-triggered pop-ups. Evidence collection is vital. We ensure access transaction logs accurately reflect user roles, link CCTV snapshots to specific alarm events, maintain gate and barrier safety test records, and document SOC acknowledgements and escalation processes. Remember, security commissioning isn't complete just because the equipment is installed or moved into place. It's only finished when every barrier action, alarm, video feed, access log, and operator response aligns perfectly with the established security operating procedures. This holistic approach guarantees a robust and reliable external security system. On this slide, we focus on the access control, CCTV, IDS, and SOC integration commissioning. The main objective here is to ensure that identity verification, surveillance systems, intrusion alarms, and operator responses are all properly linked and time-synchronized. The scope covers various components: ACS controllers, readers, turnstiles, mantraps, and door hardware, CCTV cameras along with recording, analytics, and video management, intrusion detection systems and perimeter intrusion detection systems, intercoms, guardhouse or SOC workstations, and alarm pop-ups. It also includes fire alarm interfaces, emergency release mechanisms, and lockdown modes. For the level gate proof process, it begins with security zoning and risk assessment at level 0, followed by factory acceptance tests and software setup at level 1. Level 2 is split into device installation readiness and individual hardware tests, including readers and sensors. Level 3 verifies user roles and alarm routing. Finally, levels 4 and 5 focus on scenario-based testing, such as forced entry, fire release, lockdown, and network failures. Acceptance evidence includes various documentation and logs, like door and reader matrices, camera coverage proofs, alarm maps, SOC event screenshots, and records of fire release and lockdown cause and effect. Additionally, operator workflow verification and escalation training sign-offs are essential. A key caution is never to commission security systems in isolation. They must be tested in conjunction with fire egress protocols and SOC operational responses to ensure comprehensive safety and security integration. On this slide, we're focusing on the commissioning process for the loading dock system, which is a critical part of ensuring secure logistics operations. The main objective here is to confirm that movement of goods and vehicles happens securely without compromising fire separation, protecting personnel safety, or breaking the chain of custody. The scope of commissioning covers several key components. These include the dock leveler, inflatable dock shelter, and vehicle restraint systems. We also need to verify the motorized roller fire shutter door, dock doors, and their controls. Additionally, traffic signage, bay lights, interlocks, and safety devices are critical to the workflow. Finally, the security system integration, like CCTV, access control systems, and the loading dock workflow, must be thoroughly tested to ensure everything works together seamlessly. The playbook breaks down the testing into levels to prove the system's reliability. Level 0 focuses on truck geometry, dock sequencing, the fire shutter mechanism, and the overall security strategy. Level 1 involves factory testing of individual components such as the leveler, restraint, and shutter. Installation and alignment checks fall under Level 2A, while Level 2B covers the testing of limit switches, safety edges, restraint sensors, and fire interface integration. Level 3 tests manual and automatic cycles, emergency stops, and obstacle detection. Finally, Levels 4 and 5 simulate real-world scenarios, like truck arrivals and departures, fire alarm activations, and security events, ensuring the entire system responds properly. To accept the system, we need solid evidence. This includes cycle test sheets and records for limit and safety devices. We document fire shutter releases and resets, vehicle restraint indications, and override logs. Security event responses recorded by CCTV and operator logs are also essential. And lastly, completion of operations and maintenance training, as well as safe use sign-offs, are necessary to confirm readiness. One important caution is that commissioning the loading dock isn't just about mechanical movement. It must also fully address fire shutter functionality and maintaining the security boundary. Overlooking these aspects can lead to significant safety and security risks. Here, we're focusing on the commissioning process for the electrical overhead traveling crane, or EOT crane, which is essential for safely lifting MEP equipment to plant floors. The objective is clear: to prove that the crane can perform these lifts reliably and safely. The scope of the commissioning covers all critical components: the crane bridge, trolley, hoist, runway beams, and end stops. We also look at the power supply, control systems like the pendant and radio controls, variable frequency drives, brakes, and limit switches. Safety features such as load cells, overload protection, anti-collision devices, emergency stop functions, and rescue procedures are also included. Additionally, inspection access, signage, maintenance isolation, and operator control are part of the scope to ensure thorough operational readiness. For the level gate proof process, we have a structured series of checks. It starts with L0, verifying the safe working load, the structural interface will loads, runway integrity, lift path, and health and safety plans. L1 covers functional factory tests, material certifications, and proof load evidence. At L2A, installation aspects like runway alignment, power, labels, and exclusion zones are confirmed. L2B involves insulation resistance and continuity testing, controls, brakes, limits, and safety devices. L3 requires no load and rated operational tests. Finally, L4 and L5 focus on proof load testing, emergency stops, power failure simulations, and staged equipment lift drills. Acceptance evidence includes the factory dossier and load test certificates, runway and structural interface sign-offs, records for brakes, limits, overloads, and emergency stops, as well as operator training and the permit to lift procedures. Maintenance isolation and rescue procedures must also be documented. A common pitfall to watch out for is relying solely on a load certificate during handover. Successful EOT crane commissioning requires trained operators and detailed lifting procedures to ensure ongoing safe operation, not just paperwork. Now let's focus on elevators, freight lifts, firefighter lifts, and BMU commissioning within the MEP framework. The main objective here is to capture all vertical transport and facade maintenance systems that directly interface with mechanical, electrical, plumbing, and life safety components. This ensures seamless integration and safe operation. The commissioning scope covers several critical elements: passenger, freight, and firefighter elevators along with their supervisory panels. BMU systems including tracks, monorails, and telescopic equipment if they fall within scope, emergency power supplies, intercom and fire recall systems, access control interfaces, as well as operator safety systems, rescue plans, and maintenance access provisions. Each of these has a vital role in ensuring safety and functionality. We verify thoroughness through a series of level gate proofs. At level 0, the focus is on code compliance strategies, load capacities, fire mode functions, power interfaces, and security integration. Level 1 involves factory or controller tests with appropriate certifications. Level 2A confirms installation readiness, shaft and track setup, landing preparations, and signage. Level 2B verifies safety circuits, fire alarms, intercom systems, power supplies, and control mechanisms. Level 3 tests functional operations, recall functions, emergency power, and rescue modes. Finally, levels 4 and 5 address fire alarm integration, power failure responses, security lockdowns, and operator response protocols. Acceptance evidence includes official authority or inspector certificates, comprehensive test logs, fire recall and emergency power testing results, point-to-point records for intercom and security monitoring, load and proof test reports specific to freight lifts, BMUs, or overhead traveling cranes, and documentation confirming user training along with rescue procedure sign-offs. A common trap to watch for is that vertical transport systems can significantly affect building egress routes, ongoing maintenance, and future equipment replacements. It's crucial to incorporate these considerations into transition training sessions to avoid operational or safety issues down the line. This slide focuses on the integrated commissioning item register specifically for security, lifts, and material handling within the data center MEP testing and commissioning playbook. The key point here is that security and material handling commissioning must thoroughly validate various operational states, including normal operation, denied access, emergency scenarios, and failure modes. Looking at the table, we have several critical assets listed, such as the access card system, CCTV system, main gate non-crash rate sliding gate, hydraulic road blocker, and swing gates. For each of these, the commissioning levels are defined by the Testing and Maintenance Specifications, or TMS. For example, the access card system requires verification of reader and lock interfaces, user roles, anti-passback features, fire release mechanisms, and monitoring through the Security Operations Center event log. The CCTV system needs to be checked for coverage, camera focus, recording quality, retention policies, analytics including event pop-ups, and time synchronization. Mechanical elements like the main gate sliding gate and hydraulic road blocker require checks on physical components such as foundations, motor drives, safety loops, interlocks, and emergency stop functions. Each asset's commissioning involves representative task pack evidence that must be documented and reviewed. Finally, it's crucial to use this register as a detailed planning and control tool. Every asset should have a unique tag, corresponding test pack, a designated evidence owner, defined witness levels, and a clear path for resolving any issues that arise. This structured approach ensures comprehensive oversight and accountability throughout the commissioning process. Here, we're looking at the integrated commissioning item register, focusing on security systems, lifts, and material handling as part of the data center MEP testing and commissioning playbook. The key point is that access control, vertical transport, and material handling systems aren't standalone. They're integrated with fire safety, security, and operations to ensure comprehensive functionality and safety. This table outlines the primary assets we manage, starting with full-height turnstile gates and pedestrian turnstile gates. For these, testing covers everything from reader interface and rotation to anti-tailgate features, forced entry alarms, safety sensors, and emergency egress, ensuring tight security and smooth pedestrian flow. Next, we have lifts and supervisory panels. Lifts undergo load testing, fire recall, firefighter mode checks, emergency power testing, and the verification of intercom and rescue systems. The supervisory panels are tested for software performance, network connectivity, alarm displays, and event logging to maintain operational oversight. Finally, the BMU monorail system is checked for rail alignment, trolley and hoist functionality, safety limits, overload and fall arrest mechanisms, and rescue procedures, critical for safe maintenance access. A crucial recommendation is to use this register as a planning and control tool. Each asset should be clearly tagged and supported by comprehensive test documentation, an assigned evidence owner, required witness levels, and a clear path for issue resolution and closure. This structured approach ensures nothing gets overlooked and helps streamline commissioning and ongoing maintenance. On this slide, we're focusing on the integrated commissioning item register specifically for security, lifts, and material handling systems within the data center. It's important to understand that logistics equipment and other operational support systems are included in this register, particularly when they impact safety, security, or maintainability. Looking at the table, we have a breakdown of key assets, starting with Yodi cranes. There are 7 of these, and their commissioning levels are defined by the TMS. The representative task pack evidence includes critical checks such as runway and hoist inspections, proof load tests for safe working loads, brakes, limits, overload protections, emergency stops, and operator training. Next, the dock levelers with vehicle restraints. There are 4 in total. We verify platform and lip integrity, restraint functionality, bay lighting, safety devices, load tests, and interlocks to ensure everything operates safely and reliably. For motorized rolling doors and dock shelters, 2 units are covered across several commissioning levels from CxL2 to CxL5. Key evidence here involves shutter cycling tests, fire close mechanisms, safety edges, shelter inflation and sealing, as well as system reset procedures. Finally, the EV charger, a single asset in this scope, requires testing of supply and earthing connections, protection devices, charger output, communications, building management system interface, and the emergency stop function. The key takeaway is to use this register as a planning control tool. Every asset documented here should have a unique tag, an associated test pack, a designated evidence owner, a defined witness level, and a clear process for issue resolution and closure. This ensures full traceability and accountability throughout the commissioning process. Here we're focusing on 3 critical aspects: heat load testing, integrated systems testing, and maintainability. These elements are essential for ensuring that the data center can handle the expected operational demands without failure. Heat load testing verifies that the cooling systems can manage the thermal output from all the equipment, preventing overheating and maintaining optimal performance. Integrated systems testing is all about proving that different systems, power, cooling, fire safety, and more, work seamlessly together, ensuring redundancy and recovery capabilities are in place. This scenario-based approach helps us confirm that the data center is truly operationally ready and can sustain reliable service even under stress. Overall, these tests are a vital part of the data center MEP testing and commissioning playbook, guiding us to deliver safe, resilient, and efficient infrastructure. In this slide, we focus on the heat load testing playbook and the essential steps involved in preparation. The primary goal here is to verify the thermal capacity and stability of the system before moving on to integrated failure scenarios. Essentially, we want to simulate the heat output from both IT equipment and the plant room to confirm that airflow, hydronic capacity, cooling controls, redundancy, and recovery functions all work as intended before the space is officially put into service. Preparation starts by ensuring all Level 4 commissioning of cooling systems is complete. Balancing has been accepted, controls trends are enabled, alarms are appropriately routed, and temporary heaters or load banks are installed safely with coordinated electrical supplies. A detailed load bank and heater plan must be in place, including the location map, circuit schedule, heat density, spare capacity, cable routing, emergency shutdown procedures, fire watch if necessary, and a thermal impact risk assessment. Instrumentation is critical. You'll need comprehensive temperature monitoring across the space, including rack and aisle sensors, return and supply air measurements, chilled water temperatures and flows, plant power, power quality monitoring, building and control management system trend points, and use of time-synchronized loggers for accurate data capture. Data setup involves capturing screenshots before and after testing, agreeing on trend intervals, preparing manual reading sheets, defining pass/fail thresholds, and setting recovery time criteria. The witness plan should include all relevant stakeholders, such as operations, commissioning agents, general contractors, controls, electrical and mechanical teams, safety personnel, and authorities when required. Before starting heat load testing, it's crucial to confirm there are no open safety issues and no unapproved bypasses in the system. During the test, all parameters must be trended continuously and every deviation carefully recorded. After the test, you compile raw data along with a summary and document lessons learned for future reference. Acceptance of the test depends on proving that capacity, controls, and recovery meet the required standards. Remember, heat load testing isn't just a superficial demonstration. It's a rigorous, measured thermal experiment with controlled variables and auditable evidence to ensure the system's reliability and performance. Here we have the heat load testing playbook and its test sequence, which is crucial for validating the performance and reliability of the data center's cooling systems. The sequence begins with establishing a baseline by operating the system under normal conditions to gather stable data like ambient temperatures, chilled water flow, airflow, and any baseline alarms or trends. Then we progressively increase the heat load in steps, starting at 25%, moving to 50%, then 75%, and finally reaching full design load at 100%. At each step, we observe how the system reacts, checking for temperature distribution, equipment staging, modulation of valves and fans, and ensuring there are no hot spots or instability. Once we reach full load, we sustain it long enough to confirm thermal stability, measure power consumption, cooling performance, and monitor alarms closely. Next, we perform redundancy tests by removing N+1 or N+2 components to verify how quickly the system recovers, ensuring no cascading failures occur and that standby systems activate properly. We also simulate control failures, such as sensor or network faults, to observe fallback procedures, operator notifications, and recovery methods, whether automatic or manual. Finally, we restore the system to normal operations, confirming that all alarms clear, set points return to standard, and any issues are fully documented. Throughout this testing, it's vital to use the project-specific warning and critical temperature thresholds, recording rate of rise and recovery times against these triggers. This approach ensures that the data center's mechanical, electrical, and plumbing systems not only meet design expectations, but also operate reliably under real-world conditions. On this slide, we're looking at the heat load testing load profile, which is essential for verifying the cooling capacity and reliability of a data center. The profile shown here is an example visual representation that includes thermal staging and soak periods. Thermal staging means we gradually increase the heat load in steps, starting from 0%, then moving through 25%, 50%, 75%, and finally reaching full 100% load. Each of these stages is followed by a soak period, which allows the system to stabilize under that specific load condition before ramping up again. The soak periods are crucial because they let us observe how the cooling infrastructure reacts and maintains temperature stability over time at each load level. It's important to note that all timings and load percentages must align with an approved script, taking into account the utility capacity, temporary power arrangements, and the project's specific acceptance criteria. This ensures the test accurately reflects real operating conditions and verifies that the data center's mechanical, electrical, and plumbing systems can handle expected heat loads safely and efficiently throughout their deployment. On this slide, we focus on integrated systems testing for electrical scenarios, specifically under the E4 category. The goal here is to prove automatic resilience during various utility, generator, UPS, static transfer switch, automatic transfer switch, and distribution events. This testing framework is a key part of the data center MEP testing and commissioning playbook. We categorize the scenarios into 6 primary families. First, utility loss events include situations such as losing utility A or B, total utility failure, or even a brief power blip during transfer or cooldown periods. The main evidence for these tests includes monitoring transfer sequences, generator start actions, UPS ride-through capabilities, power quality monitoring, and alarm responses. Next is generator resilience, which covers generator failure, N+X operations where spare generators support the load, redundant swing generators, dead bus conditions, and utility restoration. Key indicators here include start times, load sharing accuracy, breaker sequences, and capacity margins. For UPS and battery scenarios, tests simulate inverter failures, bypass transfers, battery discharge cycles, returns to normal operation, and alarm responses. Evidence is gathered through detailed UPS trend data, battery status, static transfer switch holds, and confirmation that critical loads do not drop. Static transfer switches and automatic transfer switches scenarios include loss of preferred power sources, static and mechanical transfers, return transfers, and handling source mismatches. We observe transfer times, waveform and power quality data, and downstream load stability for these events. Distribution path tests handle bus coupler operations, transformer or panel failures, feeder isolations, and breaker shunt trips where allowed. We look at topology states, breaker positions, load continuity, and the status of all protection devices. Finally, load recovery evaluates the restart of cooling systems after electrical transfers and restorations, tracking the restart timeline of equipment like CRAH units and chillers, thermal trends, and the clearing of alarms. It's important to note that all critical power transfers are tested using synchronized electrical and mechanical trending. This combined approach ensures that we assess both power continuity and thermal impacts simultaneously for a comprehensive understanding of system performance. This slide focuses on integrated systems testing, specifically covering mechanical, controls, and life safety aspects within data center MEP commissioning. It highlights the importance of cross-discipline scenarios that uncover hidden dependencies, ensuring all systems work seamlessly together. The table presents various scenario families such as cooling plant failures, airside failures, water system issues, controls network disruptions, fire and life safety events, and operator responses. Each scenario includes example scripted events and the primary evidence needed to confirm proper system performance. The key takeaway here is that the best integrated systems testing scripts simulate one credible disturbance at a time, carefully recording the automatic system response and demonstrating safe restoration. This approach minimizes risk while verifying that all systems respond correctly under real-world conditions. On this slide, we have the IST sequence diagram, focusing on how to run an integrated scenario without losing evidence or control. This is crucial for the data center MEP testing and commissioning playbook. We start with the pre-brief, where we confirm the scope, authority, abort criteria, communication plans, safety controls, and the restoration method. This step ensures everyone is aligned and ready. Next, we establish a stable baseline by capturing the system's current status, including topology, load, temperatures, alarms, and the status of BMS, CMS, EMS screens, and loggers. This baseline is essential for comparing test results. Then comes the trigger event, where we perform the approved action exactly as scripted without any unapproved disturbances to maintain test integrity. During the observe phase, automatic controls operate naturally unless safety concerns or abort criteria require intervention. It's important to watch how the system responds automatically. The hold or measure step involves maintaining the test state for a specified duration while recording the system's performance to gather reliable data. After that, we restore the system by returning it to normal configuration and confirming there are no residual instabilities, ensuring system stability post-test. Finally, the debrief and IRL include evaluating the test output to make a pass or fail decision, updating the issue log, identifying root causes for any anomalies, determining if a retest is necessary, and collecting documentation like photos and screenshots, with a named closeout owner to ensure accountability. Abort conditions are clearly outlined to protect safety. These include life safety risks, uncontrolled thermal rises, personnel hazards, unexpected critical load instability, or loss of monitoring data that would make results unreliable. To maintain evidence control, we use one synchronized time source, number screenshots, avoid overwriting raw logs, and apply clear file naming conventions to keep the data organized and secure throughout the process. This sequence ensures a thorough, controlled, and well-documented testing scenario that maintains integrity and safety at all times. On this slide, we focus on maintenance scenarios and the concept of concurrent maintainability within critical systems. The main goal here is to demonstrate how planned maintenance can be executed without disrupting the critical load, ensuring continuous operation and reliability. Looking at the table, it breaks down key maintenance areas along with what needs to be proven during maintenance and the typical evidence required to show success. For the utility or high-voltage path, we must verify that maintenance on one power source or the bus coupler strategy allows uninterrupted critical load. Evidence includes switching plans, breaker status, power quality monitoring, and alarms. In generator and fuel systems, maintenance involves isolating the generator, connecting load banks, or managing fuel transfers. We confirm maintainability through run tests, fuel transfer records, and isolation documentation. For uninterruptible power supplies and static transfer switches, it's essential to perform activities like UPS bypass or battery string maintenance without causing downstream interruptions, supported by alarm monitoring and proof of normal system return. Transformer and low-voltage board maintenance relies on isolation via alternate paths while maintaining load continuity, verified through protection settings and thermal scanning. Cooling plant maintenance, including chillers, pumps, and cooling towers, requires maintaining sufficient standby capacity to handle the load, backed by capacity margins and thermal trends. Lastly, controls and network equipment should be maintainable without loss of critical monitoring or control, supported by proof of redundant paths, alarms, and backup configurations. Importantly, for systems designed with concurrent maintainability, the playbook should include procedures for planned maintenance as formal tests, not just unplanned failure scenarios, ensuring readiness and reliability at all times. Here we have the rated or Tier 3 topology training diagram, which illustrates a key concept for maintaining critical facilities without interrupting operations. The main idea is to have one active critical distribution path that's fully supported with redundant components, along with an alternate path. This setup allows us to perform planned maintenance on the system without any shutdown of the critical load. On the diagram, you can see two utility sources, Utility A and Utility B, providing power through two switchgear paths. Switchgear A is labeled as active, handling the current load, while switchgear B serves as the maintenance path. This means that when maintenance is needed on the active path, the load can be seamlessly transferred to the alternate path to avoid any disruption. Additionally, important components like UPS and cooling systems are designed with N+1 redundancy. This means there is at least one extra unit beyond what's necessary to support the load, ensuring continued operation even if one component fails or is taken offline for service. Similarly, PDUs and CRAC units support the served critical load with this redundancy in mind. For commissioning, key evidence includes demonstrating component redundancy, proving the ability to transfer loads during planned maintenance, following isolation procedures, and confirming that no single maintenance action requires an IT load shutdown. It's also crucial that operating instructions are clear and detailed. Remember, this diagram is for training purposes and shows the general concept. The actual data center design must strictly follow approved construction drawings. This approach ensures reliability and continuous protection for critical loads during maintenance activities. On this slide, we're looking at a Tier 4 topology training diagram, which illustrates the concept of fault tolerance and independent active paths in a data center environment. The key idea here is to have multiple, physically separated active paths, each with redundant components, so that a failure in one path doesn't interrupt the critical load. Here, we see two distinct paths, Path A and Path B, both starting from separate sources and moving through independent switchgear. Each path includes redundant UPS and cooling systems to ensure continuous operation. The distribution systems for both paths are active simultaneously, often referred to as dual-cord power, to supply the critical load. This setup is designed to provide continuous power and cooling, even if one path experiences a fault. During commissioning, thorough testing is performed to provide evidence of independence between paths, physical separation, effective fault injection, automatic response mechanisms, and proof that no single event can disrupt the critical load. Restoration capabilities are also verified to ensure reliable operation under all conditions. In essence, this configuration guarantees maximum uptime and resilience by preventing any single point of failure from impacting the critical systems. Here we have the Resilience Acceptance Evidence Matrix, a vital tool for ensuring that each resilience claim made during commissioning is backed by clear, observable evidence. The goal here is to map every resilience claim directly to proof that can be verified through commissioning activities. On this matrix, you'll see different resilience claims listed, such as concurrent maintainability, fault tolerance, redundant components, independent paths, maintainable controls, and operational readiness. For each of these claims, there are specific types of evidence required. For example, to verify concurrent maintainability, you need to see documented switching plans, alternate paths, isolation procedures, and demonstration of no-load shutdown. This typically aligns with commissioning levels 4 through 6. Fault tolerance requires evidence of how the system responds automatically to single failures with no interruptions, including alarms and recovery actions, which is usually evaluated at commissioning level 5. Redundant components must show proof of component failure or removal testing, standby system starts, capacity margins, and trending data. Independent paths must be physically separate with no shared points of failure, validated through failure tests and operational diagrams. Maintainable controls focus on failover capabilities, backup configurations, local fallback options, and operator alarms, again generally validated at commissioning levels 4 and 5. And for operational readiness, it's about ensuring staff are trained, drills have been conducted, standard operating procedures are in place, and that all documentation, including spare parts lists and manuals, are complete. The key takeaway here is that resilience claims should never be accepted at face value. Always demand matching test records, trend data, screenshots, switching logs, sign-offs, or fully approved design justifications. This approach ensures the resilience of the data center can be confidently relied upon.